Hello class, welcome to this video on the 6.3 test assessment. So we're going to look at one of the versions of the test here, starting with the multiple choice. A blind taste test will be conducted with 9 volunteers to determine whether people can taste the difference between bottled water and tap water. Each participant will taste the water from 2 different glasses and then identify which glass he or she thinks contains the tap water. Assuming that people cannot taste the difference between bottled water and tap water, what is the probability that at least 8 of the 9 participants will correctly identify the tap water? Okay, so this is a binomial experiment. It satisfies bins, right? So either they correctly identify it or not, right? So binary, so success or failure. Each person is independent from the next. The number of trials is the same. Here in this case you have 9 participants, 9 volunteers. The probability of success is the same, assuming that they can't taste the difference. Assuming that they cannot taste the difference, then it should be 50%, right, for probability of success. All right, so definitely binomial, and we want the probability that x is greater than or equal to 8. So at least 8 of the participants, which means 8 or 9, okay? So, you know, you can use a binomial CDF just to make this a little easier. So we're gonna do binomial, but remember, in order to do binomial CDF, you have to convert this to less than or equal to. Okay, so what we're gonna do is the opposite of greater than or equal to is, so we're gonna do 1 minus, the opposite of greater than or equal to is less than. Okay, so less than 8. But remember that binomial CDF still can't work for less than 8. Binomial CDF can only work for less than or equal to. So it's going to be, so we're going to have to change it to 1 minus x is less than or equal to 7. Okay, and now it can work. And now we can use the binomial CDF. So 1 minus binomial. Okay, so binom CDF. All right, remember the first thing we have to identify is the number of trials. Okay, so the number of trials, n equals 9. The probability of success, which is 0.50 or 0.5, and then x value is 7. Okay, so we do 1 minus the binomial CDF. All right, so we're going to show you here. You hit second, vars, you can go down to binomial CDF right here. You got 9 trials, 0.5, and x value of 7. All right, and we got there for that's my probability, and then we got to do 1 minus that, of course. We have 0.0195. All right, so in this case we got 0.0195, and so the answer is B. All right, so number 2, a popular computer card game keeps track of the number of games played and the number of games won on that computer. The cards are shuffled before each game, so the outcome of the game is independent from one game to the next and is based on the skill of the player. Let x represent the number of games that have been won out of 100 games. Under which of the following situations would x be a binomial random variable? All right. All right, so part A, all games were played by the same player whose skill improved over the course of the 100 games. No, that wouldn't be true because now the probability of success changed and it's no longer, you know, no longer independent, right? The probability changed over time. So not A. A group of 5 players at different skill levels were each allowed to play 20 games. Again, different skill levels, so that means different chances of success. Group of players of different skill levels were each allowed to play until they had lost 3 games, and this resulted in 100 games. So again, allowed to play until so that means that the number of trials is not the same, and they have different skill levels. 2 players of equal skill level played 1 game a day for 50 days, and their skill level did not change from day to day. So there you go, 1 game a day for 50 days and their skill level did not change. That would make it in a binomial situation, just to be on the safe side and make sure that it approximates binomial. All right. So number 3, for which of the following scenarios would it be appropriate to use a normal approximation to the binomial distribution? Where n is the sample size, little n, and big N is population size. Okay, remember, in order to be able to use a normal approximation to the binomial distribution, you have to satisfy the large counts. So np is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. All right. So so basically, let's start with the biggest one to see, or let's start with let's start with A and then see if that's too small or not. Well, 10 or 20 times 0.05 is equal to 1, which is not greater than or equal to 10, so it's not A, so that's too small. And then 30 times 0.4, that's going to give you 12, so that looks okay. But remember, we also have to satisfy the 10% condition, and 30 over 200. Let's see, 30 over 200. 30 is definitely more than 10% of 200. Let's see, 30 over 200. Yeah, so it's 15%. Okay, so that's 15% of the population. So remember, it has to satisfy those two conditions, the large counts and the 10% condition. And this fails the 10% condition. And for part C, we got 40 times 0.9. That's greater than or equal to 10. However, if I did 40 times 1 minus 0.9, that's going to give me 4, which is not greater than or equal to 10. So it fails the large counts condition, the large counts condition. Now D, we got 50 times 0.25. So that's 1/4 of 50. So let's see, 50 divided by 4, so it's 12.5. So that manages to satisfy it. And then 50 times 1 minus 0.25 is also greater than or equal to 10, so it satisfies that. And does it satisfy the 10% condition? So 50 out of 1,000 is 5% of the population. So that's good. So that satisfies both conditions. It's got to be D. In a certain region, 94% of people have a certain characteristic in their blood. Suppose a group of 45 people from the region are selected at random. Let the random variable B represent the number of people in the sample without the characteristic. So B follows a normal distribution with a mean of 2.7 people. What is the best interpretation of the mean? Okay, so we got the mean is 2.7. All right, so we want to be able to interpret the mean. So remember, the mean is is the average, right? So, but we have to do this for multiple samples. So over many samples, or over many groups of 45 people in this case, right? Because we took 45 people at a time. For all groups of 45 people, this is the mean, right? So that means it has to be for all groups. So the sort of population, okay? So for all groups of 45 people, then the average number of people without the characteristic is 2.7. Yes, because it says the number of people without it. Okay, good. So that's got to be the answer. It's got to be A. Not will have the characteristic is the average number. So it can't be B or C. All right, so number 5. A die used in a certain board game has 8 faces, of which 3 are red, 3 are yellow, and 2 are blue. Each face is equally likely to land face up when the die is tossed. In the game, the player tosses on the die until blue lands face up, and the number of tosses before blue lands face up is counted. Okay, so for example, a player who tosses the sequence shown in the following table has tossed the die 3 times before blue lands. So 1, 2, 3, and then on the 4th time it lands face up. Okay, so that's just an example. All right. What is the probability that a player will toss the die at least 2 times before blue lands face up? Okay, so this looks like a geometric distribution, right? Because you're doing it at least 2 times before it lands face up. So it satisfies fibs, right? The first occurrence of success. So you keep doing it until you get success. So the first success, in this case, the success is it lands blue. Independent, right? Trials are independent. Binary, success or failure. In this case, blue or not blue. And then probability of success is the same. All right, so it looks like it's geometric, and so we can use the geometric formula. right? Now it says probability that x is greater than or equal to 2, at least 2. And remember that we can only use the geometric CDF as if it's less than or equal to. So we got to convert this. So 1 minus the probability, the opposite of greater than or equal to 2 is less than 2. And we can't do just less than 2, so we're going to do less than or equal to 1. That way it becomes less than or equal to, and then we can use the geometric CDF, right? So we got 1 minus geomet CDF, and then we got to provide the values. All right, and then we need to provide the probability of success, which in this case is 0, or now it says 3 are red, 3 are yellow, and 2 are blue. Okay, so it's an 8-sided die, right? 8 faces, and the chances of success to get blue, right, is 2 out of 8. So it's 1/4. So that's the same thing as 0.25. Okay, so that's the probability of success here. And then we got the value of x is 1. Okay, so we can calculate this. Oh, I just realized that the number, it can't be x equals 1. It has to be x equals 2. This is too small. So so if it says at least 2 times, that means you're going to roll 2 times, and then you get blue, which means you rolled a total of 3 times. Okay, so it should be x is greater than or equal to 3. Okay, this example that they gave us, they rolled 3 times before getting blue, which means that they rolled a total of 4 times, right? So this time for 2 times has to be 3 times that they rolled. So this is going to be less than 3, which means less than or equal to 2, which means that this has to be 2. Okay, so sorry about that. I want to fix that before I continue. So let's do the calculation on the calculator for this. All right, so let's go ahead and do it. So we got 1 minus, and then we want to do the geometric CDF. So second vars, and then go down all the way down to geometric CDF, and then 0.25, and then let's change this to a value of 1. So that was 1/4, and then 2, and then paste it, and we get 0.5625. All right, so we got 0.5625, and so the answer is D. All right, so let's look at number 6. The probability of winning a certain game is 0.5. If at least 70% of the games in a series of n games are won, the player wins a prize. If the possible choices are for n are given, which value of n should the player choose in order to maximize the probability of winning a prize? Okay, so what we're going to do is, they said you want 70% of the games to be won, right? So if we have 10 games, then 70% of 10 is 7, right? So we want 7 games to be won. Okay, so then the probability of x equals 7, and we're going to use the binomial formula so you can calculate it. So the binomial formula is n choose x times p raised to the x times 1 minus p to the n minus x. Okay, now if you don't want to do the formula, you can use binomial PDF. Okay, but I'm going to show you the formula, and then I'm going to do binomial PDF just so that you know how to write it out. Okay, so we got 10 choose 7, 0.5 raised to the 7th power, 1 minus 0.5 raised to the 10 minus 7. All right, that's how you write the formula, but we can just use binomial PDF. Okay, so let's do binomial PDF for each of these, okay, and see which one's bigger. So binomial PDF, PDF is for a specific value. N is equal to 10, P is 0.5, X equals 10. And then we're going to do the same thing, dot, 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 but X equals 20. Actually, no, not X equals 20. So let's write it out. N equals 20, P equals 0.5, and then we have to do 70% of 20. So 0.7 times 20, that's 14. And then we'll do the last one, binomial PDF, N equals 100, P is 0.5, and then we got to do 70% of 100 is 70. Okay, and you calculate the binomial PDF. So I would do that if I were you and get each of the values and see what you get. But it turns out that A is going to be the answer. So that's going to be the largest, that's going to be the value of n that would maximize the probability, meaning the probability is going to be the biggest for n is equal to 10. All right, so number 7, circuit boards are assembled by selecting 4 computer chips at random from a large batch of chips. In this batch of chips, 90% of the chips are acceptable. Let X denote the number of acceptable chips out of a sample of 4 chips from this batch. What is the least probable value of X? All right, so basically they're asking for to calculate the probabilities and C. So this is X equals 0. Now remember, X is a binomial distribution where n is equal to 4, p is equal to 0.90. All right, so that's your binomial distribution. So we can use binomial PDF. All right, so binomial PDF is for a specific value. So we get n equals 4, p is 0.90, and x equals 0. And repeat that for all of these, right? So and to see, binomial PDF, n equals 4, p equals 0.90, x equals 1, and so on and so forth. And get those values for your notes. And then test each of them out. The one that's the smallest probability, that's the one that they're looking for. It turns out that the smallest probability is going to be A. If you think about it, that makes sense because 90% of them are acceptable. So having no chips that are acceptable should be the least likely option. All right, number 8. According to 2015 census data, 42.7% of Colorado residents were born in Colorado. If a sample of 250 residents is selected at random, what is the standard deviation of the number of residents? So the formula, and this is in your formula sheet, for the standard deviation of the binomial distribution. This is binomial because they're either born in Colorado or they're not. Each person is independent. The number of trials is the same, 250. The probability of success is the same, 42.7%. So it's going to be this formula right here, NP times 1 minus P. So you take the square root of 250 people times 0.427. That's the decimal here, 0.427. And then 1 minus 0.427. All right, if you do that, the answer is going to be around B. All right, number 9, a certain computer chip company has a machine that makes a large number of computer chips. Of the chips produced on this machine, 3% are defective. Miriam, the quality control inspector, will randomly select computer chips from the machine to inspect. What is the probability that the first defective computer chip, that sounds like geometric, finds is the 6th computer chip? So yeah, that sounds like a geometric distribution. So we're going to use that, okay? So the first one is the 6th computer chip. So that means P of X equals 6. All right, and then the formula for geometric distribution, we'll go ahead and write it out here, is 1 minus P raised to the x minus 1 power times P. Okay, where P is the probability of success. So let's just apply that formula. So 1 minus, now 0.3% are defective. So defective in this case is success. Okay, so 1 minus 0.03 to the 6 minus 1 power times 0.03. All right, and that's it. You just have to be able to apply the formula. So in this case, you got 0.97 raised to the 5th power times 0.03. So the answer is C. All right, number 10, the transaction history at an electronic goods store indicates 21% of customers purchase the extended warranty when they buy an eligible item. Suppose customers who buy eligible items are chosen at random, one at a time, until one is found who purchased the warranty. Let X be the number of customers it takes to find one who purchased the extended warranty. Okay, the number of customers it takes until, so this is geometric. All right. Assume customers' decisions on whether to purchase the warranty are independent, so it's independent. We got the percentage of success right here, who purchased it, right? Which of the following is closest to the probability that X is greater than 3? The probability it takes more than 3 customers who buy an eligible item to find one who purchased the extended warranty. All right, so we want probability that x is greater than 3. So the opposite of that is 1 minus the probability that x is less than or equal to 3. And we do that because we want this to be less than or equal to so that we can use the geometric CDF function, okay? So we get 1 minus geomet CDF, and then we want to say, okay, my probability of success is 0.21, and then we got the value x is equal to 3. We can calculate that and see what we get. All right, so let's go ahead and calculate it. So we got 1 minus, and then we got to do second vars, go to geomet CDF, and then we can type in this value was, what was this value again? It was 21%, 0.21, and then x equals 3. We get 0.493. All right, so we got 0.493. So the answer is C. All right, number 11, the random variable w has a geometric distribution with p equals 0.25. Approximately how far do the values of w typically vary on average from the mean of the distribution? They're asking you for a standard deviation when they say how far do they vary from average, okay? So standard deviation of the geometric distribution is the square root of 1 minus p over p. Okay, so we got to calculate that. So square root of 1 minus 0.25 divided by 0.25. All right, and we calculate that. And we should get, when you calculate that, you should get 3 around there. I think that makes sense because we got square root of 1 minus a fourth divided by a fourth. You get square root of 3/4 divided by a fourth. And then we multiply, we flip the fraction. Oh, it's got to be square root over here, not the whole thing, not the whole thing square rooted. Sorry, it's just that part. There's something. Let's fix that right there. So then it's not going to be 3. It's not going to be square root of 3 like I thought. I thought it was going to be 3 or square root of 3. But we can check it out. Just so here we get square root of 3/4 divided by 1/4. So it's not going to be as nice of a number. So let's calculate that. See what that is in that case. Divided by 1/4, 0.25. So 3.46. Okay, so the answer is 3.46. D. All right, so number 12, according to a survey about how workers get to work in Wyoming, 77% of workers get to work by driving alone, 11% get to work by carpooling, and 4% by walking. 8% get to work by other means. Suppose a sample of 200 Wyoming workers is selected at random. Let the random variable D represent the number of workers in the sample who got to work by driving alone. What is the expected value of D? All right, so they give you all this other extra stuff, but all you need is this, right? This and the 200 people. This is going to be binomial because either they drive to work, they drive alone, or they don't drive alone. If they don't drive alone, that means that they carpool, walk, etc., right, with other people. So that means that we could just treat it as binomial, and the formula for the expected value for binomial is n times p. And so here we want the mu of D where they drive alone, so that n is 200 people, and then the probability of success is 0.77. So you get 154 for the expected value. And the answer is E. All right, so E. All right, it takes care of that. So now let's go ahead and look at the free response questions. All right, so when a computer generates random digits, the probability that any particular digit in the set of 0, 1, 2, all the way to 9 is generated on any individual trial is 1/10 or 0.1. Suppose that we are generating digits one at a time and let x equals the number of digits that the computer generates to get the first 0. Determine the probability that the first 0 occurs on the 5th random digit generated. So this is a geometric distribution, okay? So you have to realize that. We want the probability that x is equal to 5. Remember, the formula for geometric distribution is 1 minus p to the x minus 1 times p. That's in your formula sheet, their AP sheet. We got 1 minus 0.1 raised to the 4th power times 0.1. All right, so it's basically 0.9 to the 4th power times 0.1, which is about 0.0656. All right. You can also use technology and use the geometric CDF function or geometric PDF function. You have to use PDF because you have a specific value. And you can say P is 0.1 and then X equals 5, and you would get the same result. Okay, how many random digits would you expect to have to generate in order to observe the first 0? So this is an expected value. So you're going to use the formula for the expected value of a geometric distribution. So the expected value, in this case for x, the formula for it is 1 over p, okay? So in this case is 1 over 1/10, which is 10. So you would expect to, on average, to generate 10 numbers before observing the first 0. Part C, calculate and interpret the standard deviation. So we got the sigma x equals, now the formula is square root of 1 minus p divided by p. So we got square root of 1 minus 0.1 divided by 0.1. And so you get about 9.487. And what this means is, to interpret it, if many random digits are generated, the number of digits it will take to get the first 0 would typically vary from the mean, by about 9.487 from the mean of, what was the mean again? It was 10. Okay, the mean of 10 digits. All right, takes care of that. So number 14, the IRS estimates that 8% of all taxpayers filling out forms make mistakes. An IRS employee randomly selects, okay, so we got probability of success there, which means that they make mistakes. Randomly selects and checks 10 forms for mistakes. What is the probability that exactly one has an error? So this is a binomial distribution because you have satisfied bins. Binary, success or failure. They make a mistake or they don't. Number of trials is the same. Each person is independent. Probability of success is the same, 8%. All right, so the probability that x equals 1. We're going to do the formula. So it's the formula. We're going to do the formula and calculator. So we have n choose x. So I'm going to write out the entire formula. So the p of x equal to x is equal to n choose x times p to the x times 1 minus p to the n minus x. And in order to calculate n choose x, you can do n factorial divided by x factorial times n minus x factorial. I'm going to go through an entire calculation, but you could do this on the calculator, okay? But I just want to show you the entire calculation. So we got p of x equals 1. We get 1 factorial, or n is equal to 10. So we get 10 factorial divided by 1 factorial times 10 minus 1 factorial. Now we know 10 minus 1 is 9, so I'm just going to replace this with 9 factorial, okay? And then we got 0.08 raised to the 1 power, and then 1 minus 0.08, which I'm going to just rewrite that as 0.92, okay? Just so I don't have to spend too much space here. Raised to the 10 minus 1 power, which I'm going to write that as just 9, okay? All right, so I'm going to do this part right here off to the side just so you can kind of see it. So 10 factorial, remember, means 10 times 9 times 8 times 7 times 6 all the way to 1. That's what 10 factorial is. But what I'm going to do is I'm going to stop it at 9 factorial. All right, and that the reason being is that then this cancels, and then just becomes 10. And then 1 factorial is just 1. So 10 divided by 1 is 10. So this whole thing is equal to 10. All right, and then we could just do 10 times 0.08 times 0.92 raised to the 9th power to get our answer. All right, I just wanted to show you that calculation so you can see that. Okay, so 10 times 0.08 times 0.92 to the 9th power. All right, but if you wanted to use the binomial PDF, then that's perfectly fine. You can just show your work you can just write binomial PDF and then write down your stuff. N is equal to, so we say the probability that x equals 1 is equal to, so you got 10 trials, the probability of success is 0.08, and then we have x equals 1, okay? And you do all that just to get an answer, and we'll get the answer. Okay, and you get 0.378, 0.378. All right, so that's for ranking 1, right? For 1 having an error. All right, so now let's look at part B. The same IRS employee announces at lunch one day that she's going to check 25 randomly selected forms after lunch. Calculate the mean and standard deviation of the number of forms with mistakes she should expect to find. Okay, so the formula for binomial is n times p for the expected value. So you had 25 times the probability of success, which is 0.08. All right, so 25 times 0.08, which is 2. And then we're going to do the standard deviation for binomial distribution, which is n times p times 1 minus p. So the square root of 25 times 1, or times 0.08 times 1 minus 0.08. All right, you do that, you get approximately 1.36. And that's the mean and standard deviation. All right, part C, the IRS employee checked 25 randomly selected forms and didn't find any mistakes. Does this provide convincing evidence to cause her supervisor to believe that she is missing mistakes? Explain. All right, so first off, you have to calculate the probability of not finding any mistakes, so x equals 0. Okay, so let's do that. The probability of x equals 0 is equal to 25 choose 0 times 0.08 to the 0 power times 1 minus 0.08 to the 25th power. All right, so, and of course we're not going to do that. We're just going to use binomial PDF of n equals 25, p equals 0.08, and x equals 20 or 0. And when we do that, we get 0.124. All right, and then we got to compare that to 5%, right? So notice that this is 12.4%, and which is greater than 5%. Remember, if it's less than 5%, we have convincing evidence because it's unlikely to happen. If it's greater than 5%, then it's likely to happen, and therefore it could have just occurred by chance, and we don't have enough evidence. Okay, but here it says this is not unusual enough. Okay, so it is not unusual for random sample of 25 forms to not have any mistakes. Because 12.4% is greater than 5%. Therefore, it says supervisor, because we're talking about, does it cause a supervisor to believe that she's making mistakes? The supervisor has no reason to think or to be concerned, I guess, right? To be concerned that there were no mistakes. There were no mistakes found.